Thank you. So today's lecture is going to start from somewhere seemingly completely different than what we had been discussing yesterday, but we will be progressing towards the ideas, at least the concluding ideas of yesterday's talk, and it is going to be only tomorrow when the ideas from yesterday and today will at least conjecturally be united. So what we will start with is a very nice point in the history of mathematics. It's too close?
I think we just got an email.
It's your iPhone close to your...
Okay, maybe it's better now. Yeah. So we will start at the history of mathematics at some point, which I think is very interesting because you can call this the birth point of representation theory. It's not quite that, but it's very close. So it is the paper by Frobenius about the paper which defines the characters of finite groups. So this paper already has a definition of characters. It is actually not through representation, so it's a little bit of cheating calling this the birth point of birth date of the representation theory. It was a couple of years later when Frobenius understood his notion of group characters actually coming from representation theory. Originally he had some very peculiar way to define the characters, but actually his character tables of finite groups are the ones we think about today. So in his paper, which interestingly hasn't appeared anywhere, it was at that time customarily presented in front of a learned society. In this case it was the Berlin Academy of Mathematics. He gave this lecture about this, and then he said something like this, I guess in German, that I shall develop the concept of character for arbitrary finite groups, here in the belief that through its introduction group theory will be substantially enriched. So let me start with the first formula of today's talk by mentioning that, so the first thing he did, of course, after he defined the character table, he proved the orthogonality relations. That's really the crucial point why things work very well with group characters. And after that, his very first application was the formula, which is going to be crucial for us as well. It is going to be, the formula I'm going to present is a little bit more general than the one Frobenius had. The version I am presenting here is due to probably to Mednick, but this result is really kind of a folklore result in mathematics. You can find it in many places. For example, in Fried and Quine's work on the Chern-Simons theory for finite groups, and then their approach is via topological quantum field theory, which is somehow in the spirit of some of the things which we will use this formula for. So let me show you the formula. So the formula is showing Frobenius's application really was to show that the character table of the finite group carries information about the group, was that you take k conjugacy classes in the finite group G, and then you study the number of solutions of this equation that you have k elements from these fixed conjugacy classes, and their product multiplies to identity. And I'm saying Frobenius's case was the genus 0 case here, but the more general formula which is going to be relevant for us is that we also have 2G elements whose commutators multiply with the result of the multiplication of these CIs to the identity. So again, this is a well-defined problem. In any finite group, you fix the conjugacy classes of k elements, and then you have any 2G elements in the group, and then you just take this equation and you count how many solutions this equation has. And obviously, if you know the result, then it will tell you something about the group. And so he found this formula, Frobenius in the case genus equals 0, that using the irreducible characters of the finite group, you can actually derive a formula for the number of solutions of this equation. So for example, when genus equals 0 and k equals 2, this is exactly the orthogonality relations. You have two conjugacy classes. You want to count the number of points when they multiply to the identity. The only solution when one conjugacy class is the inverse of the other, and then you know how many solutions in that case you will have, and then the result this way is really just going to be the orthogonality relation. So that was Frobenius's application, and then several people used similar ideas, Mednick, and before him Hurwitz. In fact, the original Frobenius formula he used to count the number of covers of Riemann surfaces. So in the case of Hurwitz, he used only P1 and counted certain covers of P1 with a certain prescribed branching structure at some points, and then Mednick in general generalized this for any type of branching, and then also for genus G Riemann surfaces. And then the finite group they used, both of them, was the symmetry group on n ladders. So in fact, Frobenius was one of his first groups. He found the character table was the symmetry group, and Hurwitz, for example, used this character formula to count the number of certain coverings of P1. So that was their application, and today we are going to take, instead of the symmetry group, we are going to take one more level complicated groups. Namely, we will take finite groups of Lie type. We are going to take reductive groups like GLN and SLN, and we will take it over the finite fields, and then that's going to be our finite group. And then we will evaluate formulas like this. And then later I will tell you why we will do that. So we call this arithmetic harmonic analysis on G and FQ, and the reason for that our perspective on these character formulas is that really it is just harmonic analysis, Fourier, certain kind of non-abelian Fourier transform on the finite group G. So this is now GLN. Then we have G is the finite group G and FQ now. Then the history of the character table of G and FQ is nice. It was, in the case of NS2, it was done by a student of Frobenius and an American mathematician Jordan in 1907. For NS3 and 4, we had to wait almost 50 years. In Steinberg thesis, he did it for these two values, and not much later, Green actually obtained a combinatorial description of the full character table for any n of G and FQ. And then, so you have this nice combinatorial table, and then you can ask, can we evaluate these character formulas of Frobenius for these? And with my collaborators, representation theorist Emmanuel Detelli and Fernando Rodriguez Villegas, who is a number theorist, we managed to calculate explicitly these Frobenius formulas for the group G and FQ. And surprisingly enough, the combinatorics and the formulas were really using very heavily McDonald polynomials, which are some really non-trivial symmetric functions in two variables. Then what we evaluated is this character formula. So again, we use Frobenius' character formula to get the number of solutions of this equation inside G and FQ. We also had some assumption on the conjugacy classes. We didn't allow any kind of k-tuple of conjugacy classes. For our work, we allowed only so-called generic semi-simple conjugacy classes. The advantage of this assumption is then, if you have this genericity condition, you can show that these character sums which appear here are going to be somehow independent of the explicit choice of the semi-simple conjugacy classes. The result is going to be combinatorial only, depending on the combinatorial type of the semi-simple conjugacy classes. Okay, let me show you an example. And the example is going to be the case of GL2FQ. This is how we started in the very beginning, evaluating formulas like this for GL2FQ. So the character table of GL2FQ in the modern form looks like this. So we have 4 different types of conjugacy classes up here, and then we have 4 different types of irreducible characters, The values of the irreducible characters are here. These are some polynomials in Q times some roots of unities. And then if you imagine to evaluate those character formulas, what we are going to do, we are going to add these roots of unities times these polynomials. And for example, in an example, when we only have one conjugacy class, namely this central conjugacy class minus the identity in GR2. This turns out to be generic in our sense, but we allow genus to be any genus, any large G. Then what we are doing, we are counting the number of solutions of this equation. The product of the commutators equals -1 inside GR2FQ. And then the number turns out to be, after evaluating the sum of characters over irreducible characters of GR2FQ, we are really just using the first column of the character table from the previous slide. And this is going to be this nice formula, which turns out to be, well, after you evaluate the 4 different types of irreducible characters, you sum up those roots of unities, you are going to get these 4 terms, and you will have some rational coefficients here, but somehow always you are going to get a polynomial with integer coefficients. That's going to be very crucial later. For example, when genus equals 0, this formula should, and it does give 0. There is no solution. Basically, it's an vacuous assumption. When genus equals 1, there is going to be up to scalar a unique solution of the commutator being the minus the identity, which is somehow a finite group analog of the Stone-von-Neumann theorem from quantum mechanics. So again, if you then evaluate genus equals 1, this formula is going to give you 1. And for any higher genus, you are going to see some nice polynomial in Q with integer coefficients. And then soon we will give some more geometrical meaning to this polynomial. But before doing that, let's take our other example. This is going to be SLN of Q. In fact, I could have started with this because in the very first paper of Frobenius, the first non-trivial example he calculates is SL2 of P over a field, but for over a prime field. But for any Q, this was calculated by these 2 gentlemen, Jordan and Schur, in 1907, the same papers as the GR2 versions. And then interestingly, the theory is much more complicated for SLN than GLN. In fact, only very recently the full character table of SLN had been completed by Bonafé and Shoji. Then the next example I'm going to show you, this running example again, is the case as before. We have one conjugacy class, which is minus the identity, this generic semi-simple conjugacy class. Now we are going to be inside SL2FQ. And then if you evaluate the same character formula to get now the number of solutions of this equation into SL2FQ, then you are going to evaluate a formula like this, but now using the character table of SL2FQ. You are going to get almost exactly the same terms as before. You have the same first 4 terms as for GR2, except you will have one. In fact, this term comes in 2 parts. You will have 2 more terms at the end. And then I can show you from the character table of SL2FQ where this extra term comes from, because later that's really going to be your interest. What is the difference between these character formulas for GR2 or PGR2 later and SL2? And so here is how the character table of SL2FQ looks like. So basically every irreducible character of SL2FQ comes from an irreducible character of GR2FQ, right? SL2FQ is a subgroup of GR2FQ. You take an irreducible character of GR2FQ, you restrict it to SL2FQ, and most of the time it's going to stay irreducible, but in 2 cases it's going to split into 2 irreducible characters. And this splitting, when it happens, these extra 2 characters are causing the difference between these character formulas. I'm showing you the splitting, so these characters, which correspond to the split ones, over the central conjugacy class, which we only consider actually split evenly, so it's just going to be half the value of the character over GL to FQ. Later, for other classes, actually, that's really the complication. That's why Hodge and Bonafé had to work very hard. The other, on other conjugacy classes, this splitting is much more complicated. But for us, we will be only concerned with the central conjugacy classes in this talk. It's just evenly splitting nicely. And this splitting is really responsible for the difference between those character formulas. Okay, so you might wonder why I'm interested in these character formulas. This is actually the story, what happened that I had my collaborator, Fernando Rodriguez Villegas, knocking on my door in Texas saying that he can count the number of representations of the fundamental group of a Riemann surface, in this case a genus G Riemann surface, into Serre to FQ. He has this character formula, which he knows maybe from Frobenius or from the literature, and then he can use the character table to give this nice formula for the result. And then it turned out that these formulas are extremely relevant to the kind of Hodge numbers and Hodge numbers for the varieties I was interested in. So in order to understand what is the variety which appears here, it's not going to be the same moduli space of Higgs bundles we had yesterday, but they will be varieties which are very close related to the moduli space of Higgs bundles. They are called character varieties, and very quickly I'm going to define them. So the ones we are going to consider today are simpler than the general ones. We just fix an integer n larger than 1. And then we also have the usual twist with the d integer, which is co-prime to n. And we will fix also a primitive as root of unity for the twisting mechanism. So the varieties we are going to consider, we will consider over C, so they will be nice complex varieties, but we will also study them over a finite field, or rather over the algebraic closure of a finite field. So you should imagine that we are going to take these equations over finite fields, and also if you are fluent in algebraic geometry, then you can also have no problem to consider these varieties as just schemes over this ring. And this really is going to be the proper way to put things, work over this ring, because that will have then homomorphisms to both of these fields. You will be able to compare the varieties over the complex numbers and the finite fields. Okay, so the GLN character variety, then if you are a complex geometry, you can just think it's over GLN C. We just take 2G tuples of matrices inside GLN, and then we have this single product of commutators equal, which will be equal, not the identity, which would be the normal character variety when you are interested in the representations of the fundamental group of a genus G Riemann surface into GLN. You would take this is the only relation in the fundamental group. If it was equal identity, then you would be talking about normal representations, but we will be talking about twisted representations because we will want all varieties to be non-singular. So we take this twisted representation, then this is going to be already non-singular, the solution space of this, and then we will have a free action of PGLN, and the action is just the diagonal conjugation on all these elements, because we are interested in representations only up to isomorphism. And so you can think of this variety more conceptually as the variety of twisted representations of the fundamental group into GLN. So this turns out to be, that's the reason we had to twist it, is going to be a nice non-singular and affine variety, which also turns out to have a hyper here.
These are the stable ones?
Sorry?
Is there a notion of stability? Or?
Normally, yes, but we are taking a GIP quotient, but what happens, everything is going to be stable. Because of the twist, every solution of this is going to be an irreducible solution, so you are not going to throw out anything. If you were staying at the case when d equals 0, then you would have to worry about stability, and then you have to throw out the reducible solutions, and then the GIP quotient really would be non-trivial. It is just really going to be actually a PGLN this solution space is going to be a PGLN principal bundle over the quotient. So it's the nicest quotient you can imagine. That again is because of the twist we have. So this is a non-singular and defined variety, which moreover is going to have a natural complex symplectic structure. In fact, it's going to have a hyperkiller structure on it. And I'm not going to say much about this, but it's actually going to be very close related to the Higgs moduli space. And then the SLN character variety is the same kind of variety, but now we have the 2G tuple coming from SLN. We are going to now consider representations into SLN, and then the equation is the same, and then we will divide by PGLN again, diagonal action, and this is the same story as before. It's going to be a non-singular variety, and PGLN is going to act freely. So when we take the quotient, it just will be a nice quotient. We're not going to throw out anything. Everything is going to be stable. So this is a non-singular and defined variety. Again, it's going to have a natural homomorphic symplectic structure. So the last variety, of course, is going to be the PGLN variety. We will see the PGLN variety from both the GLN variety and the SLN variety. In the case of the GLN variety, we have the constants GL1 to the 2G, the torus, acting clearly on these matrices. I can multiply with scalars. This multiplying with a scalar will die in the, it will commute with everything, so in the commutator it will go away. So it will leave invariant the equation. So we will have a nice section of the torus GL1 to the 2G on the GLN variety. And on the SLN variety, you can multiply with n suit of unities, because that will not change the determinant of the matrix. You will stay inside SLN, but the equation is also going to be unchanged, so you will have a nice section of the finite group Zn to the 2G. And so let's see how then. Yes?
So these varieties look very much like Kuiper varieties. So is it indeed a Kuiper variety when you have two G loops?
Yes, it's close related. I like to think of them as the multiplicative versions of Kuiper varieties. So in fact, there is an associated Kuiper variety. We think of this as the additive version of our variety, and then there is a whole story which I will not touch on this, which shows that there should be a very close connection between Kuiper varieties and these character varieties. So for us, in order to define the PGLN character variety, we have first the torus acting on the GLN character variety, or the finite group Zn to the 2G as a subgroup of this torus acting on the SLN character variety. And then the quotient of both will be naturally isomorphic, and that's what we will call the PGLN character variety. We divide either the SLN space with the finite group, or the GLN space with the torus GL1 to the 2G. Sorry?
Is the action free or?
No, this is now trickier because the result is going to be only an orbifold. So the finite group is going to act with sometimes, generically it's going to be free, but it will have some stabilizers, and because the space is same with the torus, it's also going to act. There will be some finite stabilizers with the torus as well. But somehow this torus will act as if it was a free action, then we will study it over a finite field. Somehow it's cohomologically acts trivially in the GLN case. So now what we are going to do is exactly this. So we want to study the variety, the cohomology of the variety, and then one approach to this is arithmetic algebraic geometry. We can study the variety over a finite field, and we can attempt to count the number of solutions, the number of points of the variety over a finite field. And if you can do that from that arithmetic information, you hope to get a topological, cohomological information, and that's what's going to happen. But what we observe now, because I introduced before these equations, that of course Frobenius' character formula is exactly the formula which tells us how to count the number of rational points of these varieties over the finite field. Because it's only varieties given by one equation, it's very easy to take it over a finite field. Instead of n times n complex matrices, we will take n times n matrices from the finite field, and then we will count now the number of solutions of that equation, the commutators multiplying to to that central element in the group in the finite field. And that's going to be given by Frobenius' character formula. So for GLN, we have to evaluate this formula, which I mentioned we managed to do. For SLN, it's somewhat more trickier because you have these funny characters which split. But now it's actually done for any n by a student of Fernando Rodriguez Villegas, is Martin Merel. So we also have these formulas now. And for PGLN,
Do they stay reducible? And what you see in the finite field,
irreducible.
when you stay reducible, the representations of time.
Yes, yeah. It's the proof of representation being irreducible is for any field, I guess. So it works exactly the same way over the finite. And it's important because that's exactly how we are going to count the number of points in the quotient. We are going to count the number of orbits up there, and because the action there is going to be free, because everything is irreducible in the quotient, you are not throwing out anything. Exactly as over the finite fields. In fact, it is enough to count points of the equation, and then the result is just divided by the number of points of PG and FQ. It's a little bit technically non-trivial, but basically that's the idea. Everything works exactly the same way over a finite field. Okay, and in the case of PGLN, that was my comment before, is that although that torus did have some, it didn't act freely, but cohomologically the action was trivial, and so you can actually, the number of points on this variety is just the number of points in the GLN variety over q minus 1 to the 2g. Okay, and so what we notice in all these calculations which you can do, what you find is that the result, which is a priori only some sum of characters of groups, and then you will have these roots of unities, it's not even clear that the result is going to be a polynomial, or is it going to be a polynomial of the rationals. It turns out it's always a polynomial over the integers. In all of these cases, the count of these varieties is going to be a polynomial. So we are now in the case when the varieties are non-projective, so it's not entirely clear what kind of cohomological information you can get from the number of points of a variety. These varieties were projective. Of course, we could use the Weil conjectures, but in the non-projective case, the setup is somewhat trickier. And it turns out that in the case when the variety over a finite field has a number of points, which as a function of q is a polynomial, just like in our cases, then it turns out that that polynomial has a cohomological significance. So in order to explain that cohomological polynomial, I have to talk about Hodge numbers of general complex algebraic varieties, and then the Serre-polynomia, which is some generating function using those Hodge numbers. So if you have any complex algebraic variety, then Dunning constructed a weight filtration on the cohomology of the variety, which is some additional structure which we don't see for, say, on the cohomology of a manifold. Here I am, for convenience, I'm going to take compactly supported cohomology. So you have this weight filtration, this very nice extra structure, and then this weight filtration is the one which is needed if you want to talk about Hodge numbers, because it's no longer true that the cohomology groups will have nice Hodge decompositions, but the graded pieces of the weight filtration will have a natural Hodge decomposition attached to them. And so you take the graded pieces of the weight filtration, and on this you will have a weight k Hodge structure. You have a Hodge decomposition into these ij type of spaces, and then the dimension of them is what we call the mixed Hodge numbers, h, I, and j. But now we have to remember the degree as well, because it's no longer true that I plus j equals the degree. In general, I plus j will only be the same as the weight of the cohomology class. So we have now 3 variables for our Hodge numbers, and so using these Hodge numbers, we can now form what is called the Serre-polynomial. So it is some generating function of alternating sums of these Hodge numbers. So this is this should be k, and this should be k. I am sorry, I messed it up here. Yeah. So this is not I plus j, although it was I plus j k here. I should have probably taken this d, and then this one is also d. So you take this cohomology group. On this you take all the possible weights and Hodge numbers, and then you add them up. These Hodge numbers where the degree, which now is k, unfortunately it was previously, it was the weight. And then you have this alternating sum, and that's going to be the Serre-polynomial. So anyway, this is some combination of these Hodge numbers, and the interesting thing about this, that's why Serre really noted that during his construction yielded this, that they behave very nicely, these Serre-polynomials. The amazing thing about them is that they are additive. If you have the composition into locally closed subvarieties, amazingly the Serre-polynomials just add together to give you the Serre-polynomial of the total, or the big variety, or it's going to be multiplicative if you have a locally, Zariski locally trivial fibration, it's going to just multiply. So it's a very nice invariant. In fact, the way how it behaves is very much like you would expect from the count of a variety over a finite field. And indeed, it's going to be the case that for polynomial count varieties, the Serre-polynomial will have a very nice arithmetic meaning. So namely, this is the result of cuts, that if you have a variety which say is defined over the integers, which really just means that the equations defining the variety are integers, and that's very convenient because you can consider the variety both over the complex numbers or modulo p in the prime field of p, or any finite field of q. And then you can now count the number of solutions of your variety, that is the number of solutions of your equations over a finite field, and then you can find that this count as a function of q is a polynomial in q. It happens fairly rarely, actually, so of course already an elliptic curve will have a very crazy count function. It's clearly not going to be a polynomial, but for our varieties, for example, the result is always going to be a polynomial. And so for polynomial count varieties, we have this very nice relationship between the Hodge numbers of the variety over C and the discounting polynomial over finite fields. Namely, the result is that if you take now the variety over C as a complex algebraic variety, this Serre-polynomial is going to depend only on x times y, and in exactly this way, you just substitute into q x times y into the count polynomial. So it's a very nice result, because using arithmetic, you have a straightforward formula for the, not just for the Hodge numbers, unfortunately, but for this alternating sum of Hodge numbers, this generating function, this polynomial. So let me then say that for all character varieties, it is the case, they are always polynomial count, so this count is going to give these Hodge numbers. Namely, the Frobenius formula is going to give their Serre-polynomial. So for example, the calculations we have just made, when n equals 2, I guess, okay, d equals 1, and by which I mean this d, which is the degree, then in these formulas you will always have to substitute x times y into q. So then the Serre-polynomial of the PGL2 character variety is going to be the same as the number of points of the variety of a finite field, because it's a polynomial. Then this polynomial can be calculated by taking the GL2 character variety, counting the number of points of that over a finite field, and dividing by the number of points in the torus, q minus 1 to the 2g. And the result is going to be given by our calculation from before, which again turns out to be a polynomial. And this is then now not just the count polynomial, but this is the Serre-polynomial of the variety. And similarly for the SL2 variety, our calculation gives that it is the first four terms are the same as for the PGL2 variety, but we have in fact two more terms, and they look like that. Okay, so that's very good, because now we can actually compare the Hodge numbers of the PGL2 and the SL2 varieties. And then we are going to do exactly the same thing as we did for Higgs bundles yesterday, we are going to take these stringy Hodge numbers for the orbifold of the PGLN variety. So again, now I will give a little bit more definitions than yesterday. So we take a non-singular algebraic variety, complex algebraic variety. We have a finite group acting on the variety X, and then we will define the stringy Serre-polynomial of the orbifold of this by the formula that the stringy Serre-polynomial should equal the sum over the conjugacy classes of the finite group, and then you will have what we call twisted sectors, and the twisted sectors in the orbifold are going to contribute into the Hodge numbers, or in this case into the stringy polynomial of the orbifold. Again, in the definition, unfortunately, we need to include a germ, an orbifold germ, and the orbifold germ will appear as a local system on the twisted sector gamma. And then you can calculate the Serre-polynomial of these subvarieties, the orbifold subvarieties, twisted sectors, and we have to then shift everything with the same fermionic shift as we had yesterday. So this is the definition of the stringy Serre-polynomial, and the significance of this from the mathematical point of view. From the physics point of view, the significance is that this is telling us that this is the right Hodge numbers, the right Serre-polynomials you should consider for an orbifold. But from the mathematical perspective, the significance of this is a result of Kontsevich, or at least initiated by Kontsevich, that if you have a Crepon resolution of an orbifold, then the stringy E-polynomial of the orbifold is going to be equal with the Serre-polynomial of the Crepon resolution, irrespective of which Crepon resolution you take. So that's really mathematically a nice motivation to consider. But now we can, of course, notice that the PGLN character variety itself is an orbifold with now a quotient, which is the finite group, which is an abelian group. So here, in fact, you are going to have a sum for all elements of the group, not just conjugacy classes, because it's a commutative group. And then, as you might expect, what we will call the Betti version of the topological mirror test is that the stringy E-polynomial of the PGLN character variety should equal the stringy Serre-polynomial of the SLM character variety. It's exactly the same statement, at least on the level of the stringy or of these Serre-polynomials as we had yesterday about Hodge numbers of the Higgs moduli space. But in the case of character varieties, we have this technique of using the character tables of finite groups of Lie type, and indeed I can show you how this now works, how you can prove this identity, for example, for n equals 2. So the proof is very simple because we have already done these calculations earlier today. So the example is this, that so n is 2 now, b equals 1. Then we notice the difference between the Serre-polynomial of the SL2 character variety and the PGL2 character variety is exactly this term. There is this factor now, which should make sense. This 2 to the 2g minus 1 is exactly the number of non-trivial elements in our finite group Z2 to the 2g. And indeed, in each individual element, gamma, non-trivial element inside the capital gamma, the twisted sector we can identify as a torus of dimension 2g minus 2. And then you can also understand what is going to be the local system which arises from the germ. And so you will see that the contribution of the stringy contribution from this twisted sector is going to be only the odd cohomology groups going to contribute because of this twist. And so you will get this Serre-polynomial for the contribution, the stringy contribution, which is going to match exactly one of these terms. Here, q to the 2g minus 2 will be given by the fermionic shift, and then you are going to have exactly 2 to the 2g minus 1 non-trivial elements inside your finite group Z2 to the 2g. So this way, you manage to match all the elements, and then you can conclude that the stringy Serre-polynomial of the PGL2 character variety indeed is the same as the Serre-polynomial, the SR2 character variety, by just doing calculations with the characters of finite groups of Lie time. So in fact, this technique is better in that you can generalize this for higher n. When you do n equals p prime for any higher prime, then you can deduce the same result. You have the Betti version of topological mirror test by basically an equivalent calculation. And then we are very close to prove this now for every n with Martin Meret, who did the SLN calculation. We are starting to understand these contributions for when n is not a prime. So, and it seems that we are going to have the result, but it's still ongoing work. But when n equals a prime, at least, this is already better than what we could do with Michael Tadeusz for the moduli space of Higgs bundle psi. So in this last slide, I'm going to now compare this Betti version of the topological mirror symmetry with the one yesterday, and tomorrow I'm going to really give a more conceptual, at least conjecturally, a more conceptual connection between the two topological mirror tests. So what is the connection between the character variety and the Higgs moduli space is the following. So as I mentioned, both of them are hyperkähler, and if you like, they are actually the same hyperkähler manifolds, just in different complex structures. There is a very nice theory due to Simpson, where you can think of these varieties as non-abelian Hodge, non-abelian cohomology groups attached to the Betti and the Dolbo version, and in that theory, the non-abelian Hodge theorem translates to the fact that the character variety always going to be naturally diffeomorphic with the Higgs moduli space, and in fact there is going to be, as I said, this identification of the hyperkähler structure of the two. So you will have on both the hyperkähler metric, which is the same. You're just seeing the same manifold in different complex structures. Okay, and if you believe this much, then now you can see that in fact we could have used the character variety in the place of the Hitchin, in the place of the Higgs moduli space, because if you now consider the Hitchin map after this diffeomorphism on the character variety, then the Hitchin map is going to be a special Lagrangian fibration for the natural homomorphic symplectic structure on the character variety. And then you have the same story. You have these dual special Lagrangian fibrations with generic compact tori, which are dual to each other. So again, you can argue exactly as before that you have a Schrödinger-Yau-Zaslow construction. So you would expect then to have some relationship between their Hodge numbers, and this is what this topological mirror test in the Betti version is telling us, that there is some agreement of the Hodge numbers on the two sides. Tomorrow I'm going to explain what's the connection between this topological mirror test and the one in yesterday, when we had the Hodge numbers of the moduli space of Higgs bundles. But today let me just finish by saying that today we managed to prove, in the case when n equals 2, the topological mirror tests by studying something which is very classical. Namely, we studied the character table of GL2FQ and SL2FQ. And in fact, the certain patterns, the differences between the character tables was really the reason why our topological mirror tests were satisfied. And then, as I say, they are very classical because it's more than 100 years since people have described these character tables. So to conclude, I really wanted to show you something historical. So let me show you the original papers, first of Jordan, where he describes the character table, not of GL2, I couldn't find that, or maybe I overlooked this because the language you see is somewhat different than the one we use today, but PGL2, I believe. So Jordan's character table of PGL2 from the American Journal of Mathematics from 1907 describes the character table of the binary linear fractional group in the, okay, this is clear, this is a finite field Q of all determinants non-zero. So I think this is PGL2FQ he's talking about. Looking at the character table is better because it's of course it's somewhat differently written, but it actually should be the character table of PGL2FQ. So this Jordan is not the famous Camille Jordan of France, who has many other things he proved. This is basically his thesis, and I don't think he really published anything else. And then finally, let me show you the character table of SL2FQ as determined by Frobenius' student Schur. This is, I think, Relle's journal, and this is going to be in German, but this is also very interesting. He calls the SL2FQ is some linear substitution group with determinant 1, so I assume this must be SL2FQ. And in fact, it agrees, I think, with the character table we had seen. Here are these funny characters, right? The ones which split into two when you come from GR2. And somehow these classical formulas somehow here already have the traces of the mirror symmetry formulas we managed to prove. Okay, thank you.
Any question?
But I mean, your mirror symmetry test, topological mirror symmetry test, didn't you say that you proved it for all primes or what?
For all primes, we can also prove the agreement of the E polynomials or the Serre-polynomials.
But why was it only n equals 2 for?
Sorry?
On your slide it was n equals 2.
So we did only the calculation in when n is 2, but when n equals a prime, the calculation is very similar. So then again, you will have several of the characters splitting into p equal types, and then the calculation of the SLN side is going to be analogous. And then the stringy side is going to be similar again. And then the same arguments actually work for when n is a prime. The issue is going to be when n is not a prime, then things are going to be combinatorially much more complicated. And we are in the process of understanding that, and then I think we can do that too, but so far it's only n is prime, which I can claim as a theorem.
Is at 7, and we leave from the elevators on the P level at 6:45. So far we have 2 cars. That should be enough. It's a Mirabel Tower.